Okay, good afternoon, and hopefully those online can hear us too. Thank you all for coming to this Leeds Institute of Fluid Dynamics colloquia, and I'm really pleased to welcome Henry Burridge today. So, Dr. Henry Burridge from Imperial College. I've known Henry for about 8, 10 years, something like that, quite a long time now. Henry started life in financial services, working in as a stockbroker, and then he saw the light and realised that fluid dynamics was a much better place to be. And you did a PhD at Cambridge, was that
right? Imperial.
Imperial.
Postdocs at Cambridge.
Sorry.
That's right.
Imperial postdoc at Cambridge. I first met Henry when he was at Cambridge, when he set up the low energy ventilation network, which then got some funding and became Future Urban Ventilation Network. And over a number of years, Henry's now a senior lecturer in Imperial, and has worked on a lot of projects ranging from the real sort of fundamentals of fluid mechanics of ventilation in buildings through to the real practical challenges with measuring this in the real world, including the SAMI project, which you will talk about today. And Henry's also been involved in sort of giving advice to government, particularly done a lot of work with the Department for Education. So great to have you here. Hand over to you, Henry, and looking forward to hearing about fluid mechanics of buildings.
Thank you, Kath. Kath, brilliantly summed. I had not told Kath what I was going to talk about, but she basically summarised exactly what I will talk about. So I just want to start by saying, I'm going to talk about really quite a high-level overview of mainly 3 PhD projects, one by Tom, one by Caroline, and one that Pooh has just submitted. And then I'm going to talk a bit about some work that I've done with Josh Finneran, who's at Loughborough now, and Sam Wood completed some deployment of the methods that Josh and I developed, and Graham and Martin helped supervise all of these PhDs between us. So we've always spent time indoors, but we've never spent as much time indoors as we do now. And where you look, you get slightly different estimates, but it's a large chunk, 80 to 90% of our time indoors. And that means that our time indoors has enormous consequences in a number of ways. And the first of which is our energy consumption and the implications for our planet, and what we increasingly call net zero. In the Western world, we consume at least 40% of our energy in buildings, and a big chunk of that is used just to condition the indoor environments that we experience. And so you end up realizing that we consume about 20% of our total energy budget just in conditioning our indoor environment. So really important factor for net zero. Our time indoors also has consequences for our health. And those health outcomes are derived from the exposures that we have indoors. And this review, they attribute around 3 million deaths per year to indoor air. So it's very significant. So the time that we spend indoors has massive impacts on our health and well-being. And I think that's something that, research is starting to unpack more quantitatively as we look forward. Crucially for economics, it also affects our productivity. We know that going from poor air quality environments to good air quality environments improves our cognitive function and productivity. And we've already said that indoor environments are really crucial for meeting net zero. So these are all really big motivators for research and also levers for change, but they're not all well used. And I think, when I met Kath really changed the way I think about buildings to think, from a human-centric perspective. So when I think about indoors now, I try and think about the occupants that might be there. I think about the likely exposures that they'll be subject to as a result of the indoor conditions and scalars there. And when we start to think about scalars, here we're including things like heat, moisture, and pollutants. But if we want to really know and predict what people's exposures are, indoor exposures are, we'd need to know who and where the occupants are and what they might be doing, because their activities both change the production of pollutants and also change their breathing rate. And then we need to really have some way of estimating what scalar concentrations they might experience. That might be, the temperatures that they feel or the pollutants that they might be breathing. So the first point is really interesting and something worth exploring. But the second point, what are the scalar concentrations that I'm really going to start focusing on today? So in our field, we band around this word ventilation all the time, but I think it's worth defining it, and I do so as the exchange or refreshing of indoor air with air from outdoors. And there's this little schematic that illustrates nicely. This is not an exhaustive set of scenarios, but three very different scenarios of ventilation, which you can instantly see would have different marked differences in the flows and exposures. So if we want to estimate the scalar concentrations, we need to think about the indoor sources, but we also need to think about the outdoor sources of scalars, and then the ventilation rates that might bring those outdoor scalars in. And then as the ventilating flow leaves, it will be providing some dilution. So two of these aspects are really dominated by ventilation, and that's what I'm going to focus on today. So we classify ventilation based on the forcing across the building envelope. And when it's driven by fans, we call it mechanical ventilation. When it's driven by wind and or buoyancy, we call it natural ventilation. And when we have a bit of forcing from each ventilation type, we call it hybrid ventilation. And if we think about buildings, really everything's hybrid. You always have some extract, often in bathrooms. And whenever you open a door, you always drive a natural ventilation flow. So it's worth zooming in to the room scale to really carry out some more detailed thinking and research. And it's worth noting that indoors is almost always at a different temperature to outdoors. Because we want to move around our buildings, we always have doors. And so we always drive naturally ventilated flows across both open doors and open windows. So I'm going to talk predominantly around natural ventilation flows. So our understanding of natural ventilation flows really owes a lot to the work done in the 80s and 90s, this seminal work by Linden, Laneser, and Smead, looking at buoyancy-driven displacement ventilation. But it's worth reflecting that actually that builds on work that was first done in the 30s to 50s on natural convections and plumes. And it was Baines and Turner who really in the 60s thought to put these flows inside boxes. And it was that idea of translating this box model work into an analogue of rooms that really pioneered this study of natural ventilation. So these are academically very worthy, and we've learned a lot of useful things from them, but they are highly idealized flows. So I want to very honestly explore the potentials and limitations of these approaches and I do so by some work that we've done. So we're going to keep things really simple and only think about steady state ventilation flows in an isolated room. We're going to have one door and one high level opening. And then we always have heat sources, but we're going to start by idealizing these into a single local heat source. So what might we get in this simplest case? Well, if we look at Linden Lane, Surf and Smead, they had a high and low level vent, and they got a stratification at some height h. And because we're steady state, we conserve volume and buoyancy fluxes, and that tells us that the upper layer must be well mixed. We expect that there's going to be a turbulent plume formed in the lower layer. And the equal and opposite ventilating flow in and out must be equal to the flow in the plume at the height of the interface, because there is no flow across the interface outside of the plume. So if we know the height of the interface h, then from plume theory, we will know the ventilation flow. And the other body of work that's relevant to this configuration I'm going to talk about are these balanced exchange flows. Here we've got a doorway and no other ventilation openings. So the inflow and outflow across the door must be equal and opposite. And crucially, the physics is such that we can assume the interface height at the door is equal to the interface height at the room. So when we look at our example, we have part of the outflow going through the top vent and part of it leaving through the top of the doorway. And we call this an unbalanced exchange flow because the doorway exchange is not equal and opposite. And it means that we can no longer assume that the interface height at the doorway is equal to the interface height within the room. And it turns out Tom did some nice experiments and realized there's at least 3 flow regimes. This is the classic Linden Lane surf displacement ventilation, where the interface forms above the doorway because either the room is tall relative to the doorway or the top vent is large. Change things so that the interface comes down within the room. You can get an arrested doorway flow where the interface is below, but the characteristic buoyancy speed is less. The characteristic buoyancy speed out is less than the characteristic ventilation velocity coming in, and it arrests the flow. But we're going to focus on this third type, the unbalanced exchange flow, which I just described to you. So as is standard in building fluid mechanics, we assume air to be incompressible and the flows to be Boussonesque. We take the pressure to be hydrostatically distributed away from the vents, and the steady state imposes that this upper layer must be well mixed. And then we can start writing down key facts. One is the description of the flow in the plume at the height of the interface. We then rest on the concept of a neutral pressure level, which when you think about it, the pressure distribution inside and outside the room are such there must be a point within the height of the room at which the pressure is equal inside and outside of the room. And that height we call Hn. And it's the buoyancy potential above that height that's going to drive the flow through the top vent. And the difference between the neutral pressure level and the height of the interface is set by the energy head loss of the inflow, which we take to be fully dissipated in the lower layer without consequence. And then we need to lean on 2-layer hydraulic flows to look at a composite Froude number and know that must be unity. We shove all of that back into our conservation of volume, and we end up with one equation, but we have 2 unknowns, our interface height in the room and our interface height at the doorway. And so we need more. And we go to look at the energetics of the layer, the two layers, and we look at the energy head difference between the lower layer and the upper layer. And we do so at the door and in the room. And then we ask, what's the change in the energy head difference between the doorway and the room? And we argue that must be set equal to the loss of kinetic energy head in the incoming ventilation flow. And this gives us another equation. We reuse our Froude number, we rearrange our plume theory, and now we have a second equation, again in our two unknowns. And so we have a closed system, and we can predict the interface height. So the question is, how good is the model? So Tom does some experiments. You can see over here on the right, he's tracking the interface height, going through some transients, starting to settle to a steady state. In the black, a nice quantitative evidence of a relatively sharp two-layer stratification. And this interface height is heading nicely towards the theoretical prediction. And Tom here has chosen a dimensionless doorway width, and then shown data for 5 different dimensionless door heights. The markers are his experimental data, and the appropriately colored lines are the theory for that configuration. So the model works well. What does it mean for ventilation? Well, if we had an unbalanced, if we took this particular configuration, we had a balanced exchange flow at the door, so no top vent, then our ventilation flow would be this dotted line. On the horizontal axis, our all other data indicates the size of the top vent, and this dashed line, this dashed curve, is the result of a prediction from a classic displacement flow. The new theory predicts this blue solid line here, and at the maximum, we're able to predict a ventilation flow for the unbalanced exchange flow, which is about 30% larger than would be achieved in either a balanced exchange flow or the displacement ventilation case. So after all of this, what have we really learned? And I think my takeaway message is that even the simple, think about the simplicity of the configuration. It's not simple to analyze by any means. And then reflect that we arbitrarily chose to localize all of our heat inputs into a single point. Well, what happens if we had gone the other way and said, well, let's just uniformly distribute our heat source all over the floor? What's going to change? And so I'll show you a video of this, but the important thing to say is you can think of this as being a heated floor, and you've got a top vent up here and a doorway up to about this height. The crucial thing here is that before I start the video, Tom has spent about an hour running this experiment to steady state. So all of the flow is in a quasi-steady state. About 10 seconds before I start the video, he's burst a balloon of neutrally buoyant fluid outside the door. And so your eye is going to be drawn to seeing this transient scalar evolution. But remember that the scalar is just evolving in a steady state flow. So what happens, we can start to see, call it cold air if you like, coming in through the lower part of the door, and presumably some undyed fluid is leaving through the upper part. This relatively cold air-like fluid travels along, getting warmed. It rises up this far wall, and some of this flow has enough momentum and or buoyancy that it gets carried up and out of the top vent. But what you'll start to see is that not all of this rising flow is going up the wall. Some of it is exhibiting fountain-like dynamics here, slumping back down, and we're going to start to see the dye evidencing that the flow also has an intruding gravity current going right to left in this video, and that would ultimately carry on and go up and out the window. We'll stop the video before you get to see that, but just note that the dye, at least in this scenario, is indicating that the flow is not well mixed by any means. So we've just changed to the second easiest canonical case, and things are really difficult to understand. Reassuringly, we can predict the bulk flow rate, but that's no good if you want to think about exposures. If you want to think about exposures, you need to be able to predict the in-room flow, and we can't do that at the moment. Let alone if thinking about how comfortable people feel depends on the stratification. That there's no simple modelling to explain either. So let's make things slightly simpler and go back to the displacement flow case, but we're going to keep our distributed heat source. And all the theory predicts that we should get a well-mixed room. And then Carol Ann did some very nice numerical simulations. And these were really hard because we wanted this room, which is this middle box, to be naturally ventilated. So you need these really quite large domains above and below to actually ensure that the flow isn't affected by your ultimate boundary conditions. This is the schematic of the classroom. Carol Ann's inputting heat along the floor. You can see a lower vent on this side, and then Carol Ann's going to look at two configurations: a single-ended case where the vent is at the same end of the room as the high-level vent is the same end of the room as the lower vent, and an opposite-ended case where the top vent is moved to the far end of the room. And then we're going to introduce within this breathing zone a scalar marking the CO2 emitted by 32 people's breath. And when we look at the streamlines of the age of air here, we can already see drastic differences between the single-ended case and the opposite-ended case. This part of the flow is looking quite similar to Tom's experiment. It's running along the floor and up and out. Obviously, he doesn't have a sort of outflow back over here. Carol Ann doesn't have an outflow back over here, as Tom did. But the single-sided case, we're getting a much larger whole room circulation. So if we look at the temperature and CO2, and we mark the predictions of a well-mixed model with these dotted vertical lines, open-ended configuration in blue, single-ended in red. For the temperature in the upper part of the room, we get something close to the well-mixed predictions, but then we're getting a marked cooler region for a large chunk of the room. And if you look, temperature differences of 2-4 degrees, they're really enormous, and occupants would feel that very strongly. CO2, we get a completely non-monotonic distribution with peaks in the breathing zone, very, very different to a well-mixed space. And whether we look at the CO2 distributions in the whole room, or perhaps more relevantly, just in the breathing zone, we first of all see that the distributions are wide. They're very far from being well mixed. But importantly, they differ quite drastically between the two configurations, and there's no modeling that would capture that that's being developed at the moment. And then we take a deep breath and we look at actually what we're doing. And remember that models are just models, and we're missing so much important physics in these models, and it's already quite complicated. So the three things that came to my mind are: one, in real rooms, there's a lot of additional mixing, and that can be occupant movement, which I think Kath and Andy Woods have looked at a bit in corridors. Could be opening and closing doors. Abigail Hathaway's looked at that a bit. But we need to get these things systematically built into our thinking and modeling of indoor environments. And then there's radiation. Radiation acts to redistribute heat between any warmer and cooler surface in the room. And that includes our skin. We give off about 50% of our sensible metabolic heat output as radiation. And then, of course, we've been looking at steady states, and all rooms are transient. So at best, we need to be thinking about this sort of system moving dynamically from one steady state towards another. But I'm just going to talk about one of these, radiation. And again, we're going to do some numerical simulations of displacement and ventilation. And we're just going to have a single occupant in the room. And our single occupant, so our dimensionless room height is 1 at the ceiling, and our occupant is standing up, and they're giving off heat up to about 70% of the height of the room. And if you do some simple theory, the theory predicts that you'll get a well-mixed lower layer to about 60% of the room height. And if you run the numerical model without any radiation, the temperature distribution buoyancy equivalently you get is shown here. And it's not bad. It's roughly is a well-mixed lower layer up to about 60%. But then if you run the simulation, the same simulation, just with radiation included, and we're not changing the total heat flux, we're just changing the heat flux from being all convection to being 50% radiation, 50% convection, then your temperature distribution in your room completely changes. So we have done quite a lot of work thinking about how we could mimic this. The radiation simulations take about 3 to 4 times as long to run, much more painful to set up. And so we've been thinking about simple methods to not increase the runtime if you do a bit of thinking in advance, but they're far from perfect. So for radiation, at least, I think we've got a long way to go, but I think something we will make progress on over the next years. So we've seen that the fundamental bottom-up approaches have really made huge contributions, and I'm sure they will do as we move forward. But there's a drastic gap between doing what we need, which is to be able to model and predict the environments that humans experience in our buildings, and what we can actually do based on existing knowledge. And I think that's led me to at least to reflect that we need to really embrace this top-down approach as well. And that's particularly realized because indoor environments are so easily exploited in terms of becoming a data-rich environment. And that's not been done to the extent that it can do based on modern technologies. So the work I'm going to talk about the rest of the talk has been undertaken within the SAMI project, and it's really trying to ask the question, how can we answer the question, how can we use monitored data to estimate ventilation rates? Remember, these are the key factors one of the key factors in enabling predictions of indoor exposures. So we can't measure ventilation rates directly because there's so many non-trivial pathways for flows in and out of rooms. But we can write down a really simple conservation equation for any gaseous pollutant, but only if the room is well mixed. And we know rooms aren't well mixed, so we've got to move away from this. Carbon dioxide is breathed out by all of us, atmospheric levels are relatively stable, and it's already quite well established as a tracer capable of estimating ventilation rates. But those estimation rates estimation methods are often inappropriate for operational space. So I'll just run you through these. What's typically done is you write down a conservation equation for excess CO2, that's CO2 above the outdoor ambient levels. And then you are forced to assume that your ventilation rate is constant. And if you can turn off the source, which is obviously a problem for people's breathing, then you can simplify this to a decay rate method, and you can apply it to some data, perhaps at the end, an unoccupied period at the end of the day. But that's really problematic because as people leave, they take their own heat loads with them. They shut windows and doors for security reasons. So the ventilation rates you measure are not representative of those during occupied hours. Equally challenging, we have to keep our constant ventilation rate, but we can now have a constant source and leave the space for long enough, and we might be able to approximate it to a steady state and infer the ventilation rate from that. So we're kind of stuck over here on the left, but this on the right is really where we want to be. And so we take a classroom as an example, and we think about the fact that our occupancy, our generation rates, and our ventilation rate are going to drastically vary in time. We can describe the sort of unmixedness of the room, if you like, by the ratio of excess CO2 averaged over the whole room to the excess CO2 that would be measured by a sensor at a particular location. And we can capture that in some parameter. And then our outputs are going to be our CO2 data, which we can measure. And to describe that fully, we need to solve this ODE. And all of these functions vary in time and have no known functional form. So there's no way we can think about convenient solutions. So the method really relies on identifying a period before which and after which we can say that the excess CO2 is approximately zero. So for the case of a classroom, we can think of our period as being 1 day. And then over that day, we want to be able to estimate the per person ventilation rate achieved over that period. And we decompose our variables into a period mean and a fluctuating part, but not in a classical Reynolds decomposition. A geometric composition is more appropriate here. And then we can actually solve the full equation to give this. So we can write our per person ventilation rate as a product of the fraction of occupied time times the average generation rate divided by the average measured CO2. And when we look at that steady state fraction, let's call it, we can see it's analogous to the steady state method. These prefactors, alpha, beta, and psi bar, are our integral parameters. And what are they? They're horrible. So this alpha, this captures all of the effects of the ventilation rate dynamics. This beta is a sort of a parameter that captures events that are locally either in space or time. And then this last parameter captures the impact of the choice of measurement location. forget about the detail for now and just reflect that this is an exact integral relationship that must always be true, even in the most general space. So how on earth do you go about using it? So you have to gather data for the inputs. It could be literature, survey, observations, etc. You have to choose some statistical parameterization for your input data. So, for example, this is an example of a simulation that Josh did, and this is the occupancy that he input over the course of the day. This is the CO2 generation rates associated with that day, and this was the ventilation rate that he that resulted on that day. And this is our room heterogeneity parameter over the course of the day. You can then simulate your ODE using Monte Carlo methods. And then for every single simulation, you get the measured output of CO2. You know what the numerator of your steady state fraction was for that particular simulation. And importantly, you get an evaluation of alpha, beta, and psi bar. So this enables you to quantify the distributions for all the parameters over all of your simulations, and then provide some estimate and quantify uncertainty. So broadly speaking, you can kind of think of using it in two ways. Quite a generic deployment where you choose a building typology, which we've done for school classrooms. It's quite a big body of work. I think it took Josh, well, I think it would be to redo would be 3 months maybe in another space. Quite a lot of work. You have to have data, and classrooms are good for that. You know timetables, etc. Run the simulations to get your integral parameters. And then once you've done this for a generic set, you can then use real measured CO2 data to estimate the ventilation rate. The other way is to look at specific deployments. So if anyone here has got appropriately measured data, you can use this method to estimate the ventilation rate associated with that period of measurement. The generic method would work well for sort of spaces like open plan offices, if anyone's looking for something to do. So a little bit about SAMI and how we gather the data for schools. It's a relatively novel project. We've written a couple of papers on the methodology if people are interested to read them. The key is that we really engage with schools. We gift them a nice air quality monitor. They connect it to their Wi-Fi, and then they get access to a really cool web app, so they can see all their data, play with it, and then they can do activities to engage them in air quality and learning. But also some of them provide us more detailed research data as well. The key thing is that it enables large-scale deployment and hence mass data, which is really what you need to carry out this generic deployment. The data I'm going to show you comes from one term, and I think we've got 10,000 school days data that was suitable quality for analysis. So with the project's done a lot. We've engaged 1,000 plus schools, lots of data, blah, blah, blah. The most important thing we've done, I think, as of now, is we've established the SAMI initiative. So this sort of creates a vehicle for schools to remain engaged so that they don't lose access to their web app. They can keep sending data, we can keep analyzing it. And so it's a really nice thing to nest within future research projects. So back to deploying it on classrooms. I'm not going to pretend that you don't have to make a lot of choices. Here is a table from the paper evidencing the number of choices you have to make. What's really amazing about the work that Josh did is he is incredibly rigorous, and there's more appendices in our paper than there is paper. And it's because he did a sensitivity analysis on everything. And he really showed that actually, as long as your choices are vaguely sensible, then nearly nothing matters. Like the results are really quite choice independent, and it's because of the method of integration. So there we are. I love the equation. But all of the classrooms Josh simulates, I think like 100,000 school classroom days or something. This is the distribution of our ventilation parameter. The key thing is it's not far off unity, and its standard deviation is small. Even more true with the parameter beta. The source term is really important. It provide quite a lot of variation in your estimates. So the red curve is if you know lots about how that classroom's used, you get a narrow distribution and who's using it. Sorry. If you don't, the data I'm going to show you is the C4 case, you get a much broader spread. But this is only 10% either side of the mean. It's not a killer. And then there's very little information to parameterize this. The studies that Josh found, I think about 4 of them, you get something like a 10% standard deviation in your estimates based on where you measure CO2, and that's what we took as a mean of the standard deviation. So if you run this model, and for all of these distributions that we've input, you find that the expected value of the daily mean per person ventilation rate has some pre-factor M, which we'll call a mean bias factor, and then our sort of steady state fraction. And then around that, it's normally distributed with some standard deviation. And our mean bias factor for all those examples we ran was between 1 and 1.05, and U is the standard deviation. So, but having no contextual information about the classrooms other than the UK classrooms, you get a mean bias factor of about 1.05, and you get a standard deviation about 12. So for every day, you get this Gaussian distribution based on your measurement of CO2. So then Sam takes this data. This is the data over autumn term gathered in the SAMI schools. He happens to have illustrated it based on the outdoor temperature being warm or cold, but that's incidental for this analysis in the first part at least. And then he can translate those into every day, gives a new distribution, and he can plot, instead of daily mean CO2, he can plot the distribution of daily average per person ventilation rate. And this is really important for IAQ modeling because CO2 measurements are not useful for modeling pollutants. Estimates of ventilation rates are vital in measuring for estimating pollutants. So this is a real step forward. But they're not just useful for modeling. I think we'll be able to link health effects much more rigorously to ventilation levels than we can to CO2 levels. And so Sam produced these 3 nice PDFs. The red data telling you that when it's warm outside, you're much more likely to have a high ventilation rate in your classroom. When you're cold outside, you're much less likely to have a high ventilation rate in your classroom. So this idea of predicting exposures, it's still a long way off, but it's really important for our health, our productivity, well-being, and energy outcomes. And these are all key factors. estimating the indoor-outdoor exchange is vital. That's ventilation. And the framework I present really resolves part of this challenge by providing a new method. I think I'll leave it there and allow you to read this briefly. I think this is one thing I would like to say, is that I do think that, you know, the bottom up still has to keep coming up. And I think increasingly somehow finding clever ways to nest models together and link them is really important. And then I just want to give credit where it's due and note that there are an enormous number of names on this slide. So I'm just a very small part of an effort. So thank you for listening.